So let's continue. First, I'm going to state, without proof, the famous Mityushin-Polterovich sufficient conditions for monotonicity. So the result is due to two Russian, I don't know if mathematicians or economists or both, named L.G. Mityushin. And V.M. Polterovich. And they published the result I'm going to state, without proof, in a Russian journal. It's a short paper. You don't need to speak much Russian to understand that the title of the journal is Mathematical Methods in Economics or something like this. And their paper is in Russian. But I think there are English translations online. I may have one, but I don't suggest you to look at the original paper. I think I never did, even if I have a copy. So I learned the proof, very clearly written, the proof of the result, in a book by a famous economist or mathematical economist, Werner Hildenbrand. As I say, he is, hope he is. Many years ago, he came to my department and he was not very young. And since this was many years ago, I hope I should not say he was. I have to say he is, but I'm not sure. Very famous mathematical economist from the University of Bonn in Germany. So he has a book, Market Demand, Princeton 1994. If you look at Appendix 4 in this book, it is exactly the Mityushin-Polterovich theorem with a clearly written proof. I cannot compare his proof with the original proof. I'm sure it's the same, but the way he writes the proof, to me, is very clear. But I cannot say it's clearer or not than the original proof. I can tell you that the original proof, the very original proof, is very confused because it's in Russian. But I don't know if the English version is, how easy to follow it is. The one in this book is really easy to follow, to the point that after reading it, I was able to improve upon it, in my opinion, substantially. Okay, I produced a result, which I will show you later. Without proof, I don't have the proof here. I have it at home in handwritten notes, which, in my opinion, is much better than this result. Mityushin-Polterovich condition is what economic theorists know, and they are happy enough with this result, apparently, because with the exception of my friend and co-author and patient co-author, John Kua, he is the only one who has been working after that date, as far as I know, on monotonicity of demand. He published some papers on monotonicity, so when I got my results, I was very excited and I contacted him. We never met each other before. Then he liked my results and thought it was possible to go beyond. Then he invited me to visit him at that time in Oxford, but we couldn't go much beyond. But I think my results are interesting enough. Since I am giving references, let me be specific about a book I have mentioned several times, Andreu Mas-Colell. The other authors are Winston, I forgot the initials, and Green. They had a book, Microeconomic Theory. In 1995. I also forgot the publishing house. This is a huge book in which all the basic microeconomic theory is there. So it is used in many universities worldwide as the textbook for advanced microeconomic courses. Okay. Andreu Mas-Colell. He is from my place, from Barcelona, although he spent many years in the best universities in the US, but he came back to Barcelona some 30 years ago and was hired by a very prestigious young university, one of the best in economics in Europe, called UPF, Universidad Pompeu Fabra, named after a chemical engineer, Pompeu Fabra, who was not famous because of his achievements in chemical engineering, but because he was the first at the beginning of the 20th century to create a grammar for the Catalan language, the local language used in Barcelona. Well, he is emeritus professor there in UPF. Universitat Pompeu Fabra. Then in this book, the Mityushin-Polterovich result, which I'm going to tell you now, appears as an exercise. My conclusion is that economics students are extremely smart, by far much more than me, because I would never solve that exercise. Well, maybe if you give me time enough, maybe I will eventually succeed. But when I see the statement, I see, oh my God. Well, I'll tell you the statement and then you decide if this can be left as an exercise or not. Okay? So here is the theorem. If you, this is Mityushin-Polterovich, okay? If you is concave of class C2 with a strictly positive gradient everywhere on the strictly positive orthant. Solve the partial derivatives. They should be non-negative because you know that u is non-decreasing. Should be non-decreasing if it is regular, but then we are assuming strict increasingness. For every j, so all the partial derivatives, and suppose that it induces a demand function, not just a demand correspondence set valued, but single valued. Phi which happens to be of class C1. And on top of these assumptions, we assume that minus x transpose Hessian of u of x divided by x transpose gradient u of x. This makes sense because this gradient is strictly positive, all of its components, and we are multiplying with a non-zero, well, with another positive vector because it's defined on r plus plus n. So this is positive, the denominator, and the numerator is negative or 0 because we are assuming that u is concave. So its Hessian matrix is negative semi-definite. So with this minus sign, we are getting a positive number, non-negative number, and then we assume that this is less than or equal to 4 everywhere. Then phi is strictly monotone. It's not only monotone, but strictly monotone. I mean, monotonicity, you know that phi monotone means that P minus Q, phi of P minus phi of Q is less than or equal to 0 for every PQ. Then strictly monotone means that this inequality is strict if P is different from Q. So here you get a stronger condition than monotonicity. Okay? I leave it to you as an exercise. As Mascolell and the others did. You should have used it in your quiz for, no? Do you think it can be easily solved? The demand function is the demand function induced by a utility function. I say this utility function induces a demand function. So it's the optimal solution of the consumer maximization problem. So the definition of phi is for every P, first of all, P phi of P satisfies the budget constraint and is optimal. The value that the objective function takes there corresponds to is equal to the optimal value, which is given by the indirect utility function. So that's the definition of phi. Okay, here you have a nice exercise to do. But as I said, economists appear to be happy enough with this statement. But we as mathematicians, we should not feel happy. Well, only partially happy, but not totally happy. Why not? Because there are some unpleasant things in this statement. One is the concavity assumption, which economically makes no sense. C2, well, the appearance of differentiability here, I have already mentioned several times, we have to accept because it's a powerful tool. But I would like to have an algebraic condition. I already talked about that and told you my not very successful efforts to obtain something. I obtained something, but not what I wanted to obtain. So, another thing that makes me feel a little bit unhappy is that it is if with just one if. It's not if and only if. And then there is this very strange condition because we are not used to find in mathematical statements or theorems such large numbers as 4. Okay? And what's the interpretation of this condition? Does it have any economical interpretation, or what's the mathematical interpretation at least? Okay. So, about the differentiability, I already talked about. But I will present a result later, which is my refinement of this Mityushin-Polterovich theorem, in which I substantially relax concavity and I get if and only if. Of course, what I need to do is to modify this strange condition, but to get an even more strange condition. Okay? But which makes it possible to get an if and only if statement. But the first I am going to address is I will try to understand this condition. Okay? Mathematically. Economically, I can't. In fact, economically, it doesn't make much sense either, because it depends on the specific utility function you are using. If you use a different utility function, this condition may not hold. But again, as it happened in a previous result, this condition and that condition are somehow conflicting. Okay, because concavity means positive semi-definiteness. And here you say, okay, we accept positive semi-definiteness, but not too much. There is this bound. Again, a more appropriate phrasing of this statement would be to say, if there is a utility function which has all these nice properties and is concave, and in spite of being concave, this upper bound holds, then the demand is monotone. The utility function is not given, let's say. What is given is your preferences. So you are free to use whatever representation you want. Okay. So now I'm going to give a result which says when these things happen. This result will not look very surprising to you, at least the first three statements. The fourth one not, because you already got some experience here with expressions of this type. Okay, but when I first obtained the results I'm going to describe, I had no previous experience with convex along race functions. So I'm not telling you things chronologically. So the result proposition is if U is of class C2, non-decreasing, quasi-concave, and has no stationary point, or non-critical point. I mean, a point where the gradient vanishes. I mean, the gradient never vanishes. And look, these are the assumptions weaker than those used here. I'm using quasi-concavity instead of concavity. Here, of course, if the derivatives are positive, there is no stationary point, etc. No? So, I mean, everything which I'm going to tell applies in this situation. Then, the following 4 statements are equivalent. 1, the Mityushin-Polterovich inequality is satisfied. Maybe non-strictly, but okay, with less than or equal to. Observe that under the no stationarity condition, this still makes sense because the gradient is not 0, but it has non-negative components because our function is non-decreasing. And we are multiplying it with a vector with a strictly positive component. So the denominator must be strictly positive. Okay, so still it makes sense under my weaker conditions. And second, now you will not be surprised to see what's the next statement. If you rewrite this condition by moving the denominator to the right-hand side and then also everything you move to the right-hand side, okay? Then you get almost the condition that we found to be equivalent to that convexity along race property, but there we had 2. Here we had 4. When we had 2, it was convexity of x over t. And now when the coefficient is 4, this is a very simple matter of computations that you will see. So the condition can be expressed in this way, that this function assigning to x1 xn u of x to the power minus 1/3, again, as I said, x to the power minus 1/3 means x1 to the power minus 1/3, xn to the power minus 1/3. Okay, I make the operation component-wise. So this function is convex along rays. This is very simple to see. We will see. The condition we found that this function is convex in T for fixed S could also be stated by saying that the function u of x minus 1, here it is 1 to the power x to the power minus 1/3, is convex along rays. Okay? Convexity along rays of this function is the same as convexity in T of this function for given x. Okay? So the third statement which we are going to prove comes from the previous equivalence we saw about the generators of convex along rays functions. those max type functions, max of Li times xi. Okay? So I will use that result to prove that there exists a subset U of R plus plus n union the origin cross R such that U of x equals the maximum over LC in U of C minus the max over I of Li divided by xi to the cube, and this is true for every x. So far not very surprising because it's equivalence between 1 and 2, as we will see, has a similar proof as the one we saw for the case of convex indirect utility functions. 2 implies 3 comes from the equivalence we have seen for convex Allen raised functions, but I'm going to tell you all the details. Now the fourth statement may be slightly more surprising, is that there exists a set here, but it's not the same, so I will call it U prime or V. Such that the indirect utility function is equal to the supremum over LC in V of C minus YP cube for every P in R plus plus n in fact the supremum is a maximum. I obtained this result many years ago trying to understand the nature of the Mitjusin-Polterovich inequality. And as you see, I didn't succeed because as mysterious the appearance of 4 is there as the appearance of minus 1/3 is here. So what's the meaning of 4 there? Don't know. What's the meaning of minus 1/3 here? No idea. What's the meaning that this function is a supremum of function of this specific type? No idea. These are mathematical results. They are nice. They may be useful to handle these functions, but this is quite interesting. So the indirect utility function is the pointwise maximum of a collection of cubic polynomials. These are cubic polynomials in P, but of a very particular type. The cube of a linear function plus a constant. I cannot do more. None of these equivalence statements helps me understand the nature of the Milyushin-Polterovich inequality. But, okay, they are mathematical statements. And I have here the proof. So let's do first the equivalence between 1 and 2, which is just computing second derivative. So fixed x in r plus plus n and for this particular x, define the function phi of t equal, now the relevant function, because of what? Because we know what we are going to get, no? We know the equivalence is u of t to the power minus 1/3 x to the power minus 1/3. I define this function and I take first and second derivative. So the first derivative is minus 1/3 t to the power minus 4/3 x minus 1/3 transpose gradient of u t minus 1/3 x minus 1/3. Second derivative. I have to take the derivative of a product. So the derivative of the first factor is 4 divided by 9. I incorporate minus 1/3 to this first factor. So 4 divided by 9 t to the power minus 7/3 times everything else. Plus the first factor, which was minus 1/3 t to the power minus 4/3. But now when I take the derivative here, I have again to take the derivative of t to the power minus 1/3. So which is minus 1/3. So I get here plus 1/9. And then t to the power minus 4/3 times t to the power the same. So it's to the power minus 8/3. Okay? And then, so the remaining part is x minus 1/3 transpose Hessian of u at this point times x to the power minus 1/3. I think it is correct. And then I take 1/9 everything is correct, no problem with signs. Are all signs okay? No, this sign is not okay. Let me see. No, that sign is perfect. Both signs are perfect. What's the problem? Then I take t squared over 9 as a common factor of what? Okay, from this part of this power of t, I took t squared outside, so t to the power minus 2/3 is still left here. So I put t to the power minus 1/3 here and 2 to the power minus 1/3 there. So I get x over t to the power minus 1/3 Hessian Okay, this is this term. And that term, after taking this common factor out, the 4/9 remains 4. And then I have taken t squared out, so t to the minus 1/3 remains, which I incorporate to this factor here. Very similar of what we did for a previous result. Okay, and that's it. Because if this function is convex along rays, so we are using first equivalent to second. So if this holds for every x, in particular, this holds for x divided by t. And then this expression, which is that inequality for x over t, is telling us that when you multiply by the denominator and move everything to the right-hand side, that this is not negative for every x, in particular for x over t. So you get a non-negative second derivative, which means that phi is convex. And this is our convexity along rays. Okay? Because this is u of tx to the power minus 1/3. This is classical convexity along rays, but for this function. When you multiply the variable with t, you get a convex function of t. This is convexity along rays. So first implies second, but it's also equally simple to prove that second implies first, because if this is convexity along rays, then this is non-negative, second derivative is non-negative by convexity. And then if you take t equal 1 and multiply all this with 9, then you get what you get is x to the power minus 1/3 transpose Hessian of u x to the power minus 1/3 x to the power minus 1/3 plus 4 x to the power minus 1/3 gradient of u of y of u x to the power minus 1/3 times x to the power minus 1/3 greater than or equal to 0, but this is true for every x, so make the change of variable y equal x to the power minus 1/3, which is a bijection on the non-negative orthan, and then you get this condition with y for every y strictly positive. Okay? So this shows the equivalence between one and two. Now the equivalence between two and second, between two and third. Two and second are always equivalent. This is also a simple exercise using our characterization of convexity along rays of non-increasing functions. So consider the function u naught from r plus plus n into r defined by u naught of x equal to u to the power x to the minus 1/3. Since we are assuming that u is non-decreasing, this u naught is non-increasing. And then it's clear that what we are assuming in second is that u naught is convex along rays. So second means that u naught is convex along rays. But by what we saw earlier, for non-increasing functions, this is equivalent to saying that there exists a subset u of this product such that our function u0 is the maximum pointwise over LC in U of C minus the maximum over I of Li Ci. But then U of x, which is u0 of x cubed of x to the minus 3, okay, is maximum over LC in U of C minus the maximum over I, Li times the components of x to the minus 3, which are xi to the minus 3. And everything here is if and only if. Okay? As can be easily seen. So the equivalence between the 1, 2, 3 is really an exercise, not in the Mascoley, Winston, and Green sense, but a real exercise. Okay? But what about the remaining implications? I will prove 3 implies 4, and I will leave 4 implies 3 to you as an exercise. As you see, I'm learning from Mascoley, Winston, and Green. No, 4 implies 3 is very easy. I mean, when I say it's an exercise, I mean it. Okay? If you remember all the previous theory, of course. So 3 implies 4. Let's compute the indirect utility function, assuming third. So V of P is the supremum of U of x subject to Px less than or equal to 1. This is the definition. In fact, P is strictly positive now, and so this constraint defines a compact set, because we also have the implicit constraint x is non-negative. On the other hand, U is much more than continuous. U is of class C2. So the maximum is attained. So I can write max, and let me use this notation, max over x such that Px is less than or equal to 1 of U of x. I prefer to write it this way because now I will use the expression I am assuming for U of x. So let me explain you how I proceeded many years ago. Yesterday I realized that it can be made much simpler. In fact, I would be unable to proceed now as I did because of some technical difficulties. So what I did in that time was I moved the max inside, but then it becomes min-max. Then I used Sion theorem. You know it. That says that you can interchange sup inf with inf sup as long as for the variable to be minimized, the function is quasi-convex and lower semi-continuous, and for the other one, you have quasi-concavity and upper semi-continuity, and both sets, constraint sets, are closed and convex, and one of them is compact. Okay? This is a beautiful theorem, but I could tell you now a recent, to me, much more beautiful and simpler theorem, but it's not our topic. But it's if you like minimax theorems, or if you use in your research minimax theorem, I will tell you one, which is not so popular, but which I like it very much. It's a theorem by Riccieri. Very powerful. Okay. But now, so then now with this max, I had some technical problems. Not many. I think I could overcome them, but I found a much simpler way of making this computation. Okay, so let me put the max inside. But before putting the max inside, let me things do correctly. This is not the expression. This is not the expression of u of x. I had to take maximum. So do you see here the maximum? I don't see here that maximum. Why didn't you tell me anything? So is max LC in U? Okay, I forgot this max. Of u of x. I mean, u of x is this max. So I had forgotten this. This happens when you write long expressions, you always forget something. Well, now, the next step is to interchange the two max. Two max always commute. Max and min, you need a theorem. But max and max, no problem. So I can write max over LC in U of this max that comes inside. Max of this. But with a minus sign, it becomes min. So it's max over LC in U of C minus the min x that such that Px is less than or equal to 1 max over I of Li divided by xi cube. And if you want to avoid the use of minimax theorem, you could do it, but it would be a little bit tricky because the max here is on a finite set. There is no convexity, but maybe you could consider the simplex. It can be done in a simpler way. So what can you tell me about this min-max? Can you compute it explicitly? I'm sure you can. I'm asking you to minimize the max over I of Li divided by xi cubed subject to Px less than or equal to 1. Can you solve this simple optimization problem? Don't use KKT because there is no differentiability. How can you solve this problem? Have we here in this classroom solved a similar problem sometime? Does it remind you something? When we were computing the indirect utility function associated to a Leontief utility function, we were solving the problem max the mean over I of xi over ai subject to px less than or equal to 1. This looks somehow similar. Px less than or equal to. Then what would be your conclusion? This is a compact set, certainly. I agree. No, it would not be obtained at any corner, I think, because so here this expression, this function, it's monotonic on the real line, so you can look at it as quasi-convex or quasi-concave as you prefer, as it is convenient. But since later on I'm taking the maximum with quasi-concave, I get nothing. So I say each function here is quasi-convex, then the max is a quasi-convex function too. But the minimum of a quasi-convex function can be attained anywhere, not necessarily at a corner point. So I was also yesterday considering to use this argument, but I realized that no, it's impossible. But it's actually simpler. It's not a matter of quasi-convexity or quasi-concavity. How did we proceed in this case? We said, first of all, at the optimal solution, we had equality because an x satisfying this strictly cannot be a maximizer, because then I can increase every coordinate while still satisfying the inequality and get a higher minimum. Here I can use a similar argument because it also depends monotonically on xi. Okay, so if the inequality here is strict, then I can, what is convenient to me? I want to minimize, so I want to maximize this. So indeed, I can increase every xi while still satisfying the inequality, if the inequality were strict. And then this objective function would increase. thus contradicting that we are at an optimal point. So nothing happens and I write equality here. This was the first idea. And do you remember which was the last one? The last one was to say, in this minimization, with respect to y, all are the same. For an optimal solution. Because otherwise, if let's say x1 is the smallest, I can spend more money on x1, saving it from the others, and then the smallest could increase. Okay, so no one can be the smallest. So all must be equal. Is this argument clear? Well, you told me it was. But now I can repeat the same argument here. If some xi, for some xi this quotient is smaller than the others, then I can save money by buying less of the other goods and spend that saved money on the smallest of the coordinate that yields the smallest quotient here, or now it's the largest. Okay? And then it would increase because the smallest how is it? No, I think I have to consider here the largest. So if 1 is the largest, I should buy less of this. Okay? And spend that money in the others. Or just to save that money. And then the largest would decrease. So the maximum would decrease. So it would be smaller than the minimum, which is a contradiction. I don't know. If it is not clear, I can write the details, but do you need to see more details, or is this argument clear enough? I think you would like to see the details. Yeah? So suppose, for instance, L1 over x1 cubed is greater than Li, let's say, let j over xj cubed for j from 2 to n. So this is the largest. One of them, say 1, not to introduce new indices. Then I replace x1 with a larger x1, x1 prime, larger than x1 cube, and consider, so I buy more of x1, okay? I buy more of x1. But I will buy less of all the others. X prime j will be less than xj. How much more and how much less, I will tell you if you want. But for the moment, I say I will buy more of x1 and less than xj in such a way that the sum of the pj x prime j is the same as it was with n. This is possible. Let's say I take this equal to x1 plus epsilon. Then, and I want this equality. In fact, I have that this is equal to 1, so I want still equality with 1. Then, what I need is P1 x1 plus epsilon plus sum of Pj xj, let's say minus delta. So the x prime j will be xj minus delta for some delta positive. I want still this to be equal to 1. But P1x1, this is for j from 2 to n, plus the sum is equal to 1, is equal to this 1. So what I need is P1 epsilon to be equal to or plus or minus the sum from j from 1 to n of Pj delta to be equal 0. So this tells you how to choose delta. Simply choose delta equal P1 epsilon divided by the sum of the other Pj's. This should be positive. And if epsilon is small enough, you have changed very little, both x1 and the remaining xj, so that the first component would still be the largest. So this expression would have increased, would have decreased. The largest is attained at I equal to 1. Okay? And x1 has increased, so it has decreased. So I have a solution which is smaller than the minimum, which is impossible. And this is because I assume that one, well, it's easier to understand intuitively than writing the details, but because maybe I was not clear enough, then I provided you with the details. But it's exactly the same idea that we used with Leontief. Okay, now that we know that all the components are the same, let's call them alpha, we proceed exactly as we did in the case of Leontief. So from here we solve for xi, then xi is Li over alpha to the power 1/3, but we know that the sum of the pi xi is equal to 1, so we know that this is equal to the sum of Li over alpha to the power 1/3 times pi. Okay, so this is equal to 1, so I can solve for alpha. Alpha to the power 1/3 is sum of pi Li to the power 1/3. I call this yi, and then what I got is yp, the inner product of yp. So alpha is yp to the cube. And then I get that this is equal to maximum over, I have replaced L with Y, so the set has changed, it's now the same U. I prefer to change the notation here. In fact, I changed it partially. I changed it here, but not there. So after this change of variables, L becomes Y, C becomes V, and C becomes this optimal value, which we called alpha, no? When all the components are equal, this is called alpha. And this is where the minimum is attained. So the minimum is attained at this alpha, which is yp to the cube. Is this correct? Oh, it's very late. But 14 implies 3. I see it's an exercise. We have to write nothing. We just simply to take into account that U is non-decreasing, quasi-convex, and upper semi-continuous. So U can be obtained from V. The original U, which is this one, can be obtained from V. So if V has this expression, we obtain U from V. I mean, there is only one U that produces V. Only one U if U is regular. So it must be this U. We know that this U produces V. So this is the U. Okay? So sorry I took much time than necessary. But it was in part due to the fact that you wanted to see the details about